And in past few days, we have quite a lot of talks about the statistical tools as a methodologies. And also we have some very good talks like Philippo's show class, more focused on the domain size. So now the question is, maybe you're still wondering that what we learned in those statistical tool or mathematical tool, how this can be used for our own interest science questions or using our own model, regional or even global models. So in my talk, I just want to present a few applications of the uncertainty quantification that we learned in past few days. How we can use those methodologies for regional and climate modeling with a focus on two parts. First part is more parametric sensitivity analysis. Second part is inverse modeling, calibration, or auto-tunings. So the outline in the first part is more forward modeling, like the parametric sensitivity. We use a CAM5 global model as an example. Certainly you can apply this framework to any other global model or regional model. So we include the sensitivity analysis for precipitation, including the extremes and dynamo cycle. And also I will touch a little bit about the structure error we learned from those experiments. And also I will discuss the short ensemble simulation strategy and the process level collaboration issue. And another thing we will look at is based on those new tools, how we are using a more robust way to look at the aerosol effect. Second part is collaboration or auto-tuning, which is the inverse modeling program. We still, the second part, we still using global model as an example, with a focus on a convective precipitation ratio, how we can calibrate the convective precipitation ratio. And the second portion of the part 2 is regional modeling exercise. We're using the WRF, and also we have a study using the Big 3 to try to calibrating the convection scheme in the regional model. So the difference for the forward modeling and inverse modeling is in the first forward modeling part, when we look at the sensitivity, we don't need to compare with observation. We just look at the model performance. The second part for the inverse modeling, we need observation to evaluate a model to calculate the scale score, which can feed back this information for the auto-tuning. So the part 1, CAM5 sensitivity analysis. In this study, the science question we try to address is, for example, can we identify some parameters in the CAM5 model, for example, that can dramatically influence the precipitation in the model? If yes, how does those sensitivity change with the scale, region, or season? And also, does the parameter sensitivity change with the sampling method or the accompanying parameters? In other words, those results are depending on what parameter we choose and what sampling method we choose. And also, what is the relative contribution from individual parameters versus their interactions? The advantage of this framework, this approach is because we're perturbating multiple parameters simultaneously, which allow us to look at the combination effect of 2 or 3 parameters together rather than just the individual parameter. So answer those questions certainly can help to better understand the model behavior and the physical process associated with parameter uncertainty and external forcing as well, which can guide our hand-on model tuning and optimize model performance. So this is a framework or flowchart, which I think Professor Steve already briefly introduced for the sensitivity analysis. And the first step is we have to identify the uncertainty parameters in different schemes in the climate model, either convection or PBL or radiation. And then we should try to collect the prior information of those of each parameter, including the band, lower band and high band, and also the mean or variance if possible, based on whatever source like measurements or analytical or empirical solutions. And then when we get those information, we can generate the prior PDFs like the Jason introduced. If you don't know any information, then you can just assume it's flat. If you have more information, then we can get the more realistic PDF. After those PDF has been conducted, then we can using the sampling approach. That could be a Latin hypercube or Quasi-Monte Carlo sampling approach to sample the parameter space, which can efficiently help to design those experiments. So after the parameter are sampled, then we can get the realizations of the parameter sets. Then we can start the carry-forward simulation, which is conventional simulation with a changed parameter set. And then we have outcomes. Let's say precipitation in this case. Certainly you can look at any other output variables, include like the relative forcing or temperature or whatever you like to look at. And then, because sometimes we don't know which parameters, there are thousands of parameters in climate models, we don't know which one or which dozens of parameters is more important than others. So very often we have to narrow down the parameter space. The first study probably we select more, 100 or a couple of dozens. But we have to narrow down those parameters, reduce the parameter dimension, and then we can do the exercise again with a relatively small size of the parameters, so we can do a more in-depth analysis. So then we can go to this side to do the output analysis. So for this case, CAM5, we selected, or we already actually down-selected the 22 parameters. Those parameters including those like the threshold RH, MINL, like the threshold for the relative humidity for stream from cloud, which is the macrophysics of cloud. And also we have a few parameters in the deep convection scheme, which is the sum from a deep convection scheme, like the tau, which is a time scale for convection time for the cap, and like the DMPDZ, which is a mass increment rate related parameter, and the C0 land or ocean, they're using different value, which is deep convection precipitation efficiency. And also like a few parameters in the microphysics packaging model, like the DCS is the outer convection side, the threshold for ice to snow, and also a few parameters in shallow convection scheme, which is the University of Washington shallow convection scheme. So this is two parameters. Each parameter will have a default value, which is used in the default configuration of the CAM5. But also now we have a band, low end and the high end band, based on the expert experience. So after we have selected those parameters and after I determined the bands, now is the sampling. I think we already have a couple of talks introduced about the sampling approach. This is here we're using the Latin hypercube sampling approach, and 22 parameters. We have 1100 sample sets. In other words, each parameter is sampled in 1100 times, and so each simulation we run 5 years, and we're using the last 4 years for our analysis for each simulation. This is a parameter space for parameter A and B. So we just demonstrate. We don't need to go to details. So we also generate a surrogate model which can help to quantify the variance and the sensitivities. So here we're using the GL model, generalized linear model. Certainly there are many other different surrogate models, and you can choose. And also has been discussed in past few days. I'm no longer going to the details. And actually, even it's a linear model with fitting the global mean precipitation very well versus the CAM5 simulation. This is global mean precipitation from the CAM5 directory, and this side is GM fitting precipitation. So if the fitting very well, then we can have more confidence using the GRM or surrogate model to help to quantify some sensitivity and variance. So here is the result. This is one of the key plot I may spend more time to explain. First, we have first this is 22 parameters. We already know that the parameter name is below each panel. And each panel has 3 colors, which representing black is global mean precipitation, and red is global land precipitation, and blue is global ocean precipitation. So let's see, focus on C0 land for this parameter. By the way, first observation is for those number actually above each panel is relative in percentage relative importance of the variance explained by these parameters. So the red means statistically significant. So overall observation from here is most of parameters seem that they have a red value above them, which means most of parameters statistically significantly more or less contributing to the global mean precipitation. Among those 22 parameters, we highlight 6 parameters which contribute more. In other words, is more sensitive or more important. For example, for the zero land is a parameter over land. Certainly, the land precipitation, which in red color, contribute 40% more total variance to the precipitation change. So what this means is this figure shows is basically we divided 1100 simulation into 8 groups. So 8 beings you can see. So each being of each vertical bar including 137 or 36 simulation. That's why we have a vertical bar which is represented the variance contributed by other parameters rather than C0 land within those 138 or 37 simulations. So basically this can tell you, what it can tell you, why is a precipitation anomaly, it's global precipitation anomaly. So for example, for this figure, this can tell you how global precipitation change with the value of this C0 land. In other words, we can clearly see global land precipitation will increase with the increase of the C0 land, these parameters. Why it's useful? Because when we just do the hand-on tuning, sometimes we don't have a direction, and if your model with default configuration significantly underestimates the precipitation against this observation. So here we can just tuning up the C0 land to get large precipitation or remove some dry bias. And certainly you can see also see other parameters more or less contribute differently over ocean and land. Some parameters has more impact over ocean, like this IUGG, MIN, which already briefly mentioned in the parameter table. So this is for global mean precipitation based on the 1100 sensitivity analysis simulations. So this is similar as the previous slide, but for the extreme precipitation, 95% of precipitation. So we can see much more in black color, which means for the extreme precipitation, they have less parameters really influence the extreme precipitation. So we highlighted 3 most important ones. C0 land is still here, and also DMP, DZ. And also we found the tau become more important. Tau is a cap conception time in the deep convection scheme. We can see over land, over ocean, and over global scale, the tau contribute almost half of the total variance for the extreme precipitation. So, which is not very surprising, because for the most of extreme event, which is associated with the deep convection rather than large scale or shallow or large scale stream from cloud. So another interesting thing is we can see, if you remember, for the C0 land, we can see a linear, almost a linear, monotonically variation of the precipitation with these parameters. But if you look at the tau, for both mean precipitation and the extreme event, it's not monotonically. We can see, for example, for the overland, or even over at the global scale, we can see when tau is less than 2 hours, the precipitation generally is decreasing with the tau. But after that, when the tau is larger than 2 hours, the precipitation is starting to increase, which is very useful information for us for model tuning, because sometimes we not only focus on precipitation, we also have to take care of other aspects. So here, at least it can tell us to get good precipitation or reasonable precipitation or extreme event, we can have different tau values, can get the same mean precipitation or extreme precipitation. Another implication for this relationship is that let's say we look at some aerosol effect or greenhouse effect. The traditional way to look at the aerosol or greenhouse effect is we do 2 experiments. One is so-called control experiment, in which we not change the CO2 or aerosol concentration. Another experiment is so-called sensitivity experiment, in which we either doubled or increase the CO2 or aerosol concentration. Then we make a difference. The difference, we use the difference to represent the impact of aerosol or greenhouse gases, which is okay if we know that the response of aerosol or greenhouse gases effect is monotonically or linearly to the emission fact. But if it's not the monotonically relationship, if we like this, then we will get some trouble. You only to look at the difference of 2 experiments may not get the really impact of aerosol or greenhouse gases. We will touch this a little bit later. So this is, we just explained, we just enlarge those about the relationship associated with tau, how precipitation may change, not monotonically with the parameters, model parameters in. And this plot summarizes relative contributions of individual parameter, which is in the diagonal. The diagonal is in probability. This basically, this is basically the same, x and y, but and then this any of those is represented the interactions of 2 parameters. So we can find that for most of the interaction items, because of the 2 parameters, combination is very smaller, except then tau in some cases have contributing 5%. So the most significant contribution is from those individual parameters which are listed in the diagram. What? Oh, this is do you mean this part?
No, in the other half, it's very light colors.
Oh, this very light color? Yeah, it's very this side maybe, it's very small. And this is a summary of the result, and about the sensitivity of each parameter at different regions, different scale, different season. Basically, this is mean precipitation, this is extreme precipitation, this is phase of precipitation during the cycle. And this y-axis is different parameters, 22 parameters. And x-axis is represented different region, and like a global land, global ocean, and some small region like South America, Central Africa, and some very local region. We'd like to compare the sensitivity, how different at the more large scale, like global scale, global ocean scale, or the continental scale, like the Africa or South America, and some very local regions, see how the difference. And also each region have 3 bars represents the summer, winter, and the annual mean. So this figure gives a lot of information, but we may not go to detail, but it can tell us, again, the warmer color represents more sensitive, that parameter, or more important for the overall performance regarding the different output response variable we are interested in. So red color means more important. They have to make it more pay more attention. For example, for this tau, and but the different region may have different quantified importance. So the summary is we investigated the sensitivity of precipitation to dozens of uncertain parameters, mainly related to the cloud process in the CAM5, and we identified the different parameters for the that can more dramatically influence the model behavior in mean precipitation, extreme event, dynamic cycle, and we also found precipitation not always monotonically responding to parameter, for example, tau, and the influence of the individual parameter do not depend on the sample approach applied and concomitant parameters selected, and the total balance of precipitation is primarily contributed by the individual parameter, around 75 to 90%, and their interaction contribute to the rest of the total balance explained. Certainly, when you can easily using those framework to apply to your own model, regional or global models, you may get the different conclusions. And another byproduct from this project is we calculate the ensemble variance based on the 1100 simulations. This is spatial distribution of the variance or standard deviation. It's a similar pattern for the mean precipitation, extreme event, dynamic cycle. This is the amplitude of the dynamic cycle or the magnitude of the mix, also the peak precipitation. This is the phase or the timing of the precipitation dynamic cycle. One interesting thing we can see is, let's say, over South America, we can see the large variance for mean precipitation, extreme or amplitude of the dynamic cycle by cultivating those 22 parameters based on the 1100 simulation. But when you look at the timing or the phase of the dynamic cycle, we can see it's a very small variance or small standard deviation, which implies no matter how you're cultivating those parameters, you can change the magnitude of the precipitation, but you're not able to change the phase or the timing of the precipitation dynamic cycle over the South America and also Africa and also other land or ocean, where the dynamic cycle is very strong, associated with the deep convection. So if we look at using this plot more clearly, basically this is three different convection schemes now we are testing in our DOE climate model. And we can just focus on one, which is older Zahn-Markgraf scheme, which is default convection scheme in the CESM. And we can look at from the mountain, here is mountain to high plains, to middle plains, to the low plains, to SGP. Basically, they have a propagation of the precipitation dynamic cycle based on the observation, which is red is trim data and black is the next radar data. We can see the peak of the precipitation will be getting later and later from early afternoon to the late afternoon to the evening and even to the middle night, which is consistent between two observations. One is next radar, one is trim. We can see those propagation and there's a change of the precipitation dynamic cycle. However, you can see those dark curves are based on the example simulation we have just introduced. We can see the magnitude of the maximum precipitation will have a lot of variance, a lot of change, but the timing, they never change. They always keep in the early afternoon. So which means that no matter how you're cultivating those parameters, you're not able to improve the dynamic cycle of the precipitation in this model. Even using new developed clubbable scheme, convection scheme, or using the unicorn scheme we are testing, they have a similar issue. All those schemes not able to figure out this dynamic problem. And another second product we learned from those ensemble simulations. Actually, we have done 3 sets of PP simulations with different convection scheme. But we just introduced the focus on ZM scheme, but we also did it for the Clavel scheme and the Unicom scheme, because we are developing new so-called ACME model, accelerate climate model for energy. And we are now, one of our tasks is we try to choose which convection scheme we should use. Then we have to compare the performance of 3 different convection schemes. So if we look at for example, we look at the global length mean precipitation. This is dot is the default. This is for default simulation. We can see 3 dots with different color almost overlapped. This is usually we are doing. We compare the different model or different convection scheme. We're just using the default configuration. We're not doing any tuning. But because we have the ensemble simulation for each scheme, we can look at the PDF of the global land precipitation. And also we have observation here. Here we look at 10 different global precipitation data set. We threw away 2, extreme dry or extreme wet. Now we have 8 observations here, which is marked here. So because we know the uncertainty as well in the observation, so we have a range here from the low end to high end for the global land mean precipitation. So we can see, although the default value of the global mean precipitation from those 3 schemes are overlapped very well, but the PDF is very different. What does that mean, PDF different?
I'm sorry, you can see 2 dots, black and with red and blue, and you were saying those are 2 estimates of global mean, right?
Yeah, global land mean.
What is the global mean? So which one is the default?
Yeah, the dot is default, because default only 1 simulation line.
Okay, but then what is the red? Red is the observations, actual observed?
No, observation is here.
Right.
Observation is here. We only need to care this direction. This is the PD. This Y direction is for the PDF.
Right.
Only for apply for the.
I see. I'm just saying, what is that red in the next to the default red? What is that?
This one.
Yeah.
This is 3 dot actually also including the blue and the green together.
Okay.
Yeah. All 3 schemes generate very close global land precipitation, which may be because each scheme already being tuned very well to match the observation in global land precipitation.
Wow, and for each of them, the PDF is those 3 PDFs?
Yeah, 3 PDF is very different, because usually we never see that what the PDF look like. But this is very information for us to selecting which scheme is very good, which scheme we should use. Because this PDF can tell us the potential for the future further collaboration. For example, for those for blue, which is the ZM scheme, it's already at the high end of the PDF, this default value. So which means in future, if your model still is under predict the global land precipitation, you have no way to increase it because the PDF is already here. It's the opposite for the Clavel scheme. It's almost in the low end of those PDF, which means that if your this model Clavel scheme is overestimating the global land precipitation, you don't have too much space to decrease it because it's already at the end. But for the Clavel scheme, seems to have more potential to either increase or decrease the precipitation. So which can help us to, in another dimension to help us to compare the different scheme or even different models rather than just look at the one default value. This is the example just for land precipitation. We also looked at the other aspect like the MGO or ICTP issue, see how the different scheme generate different results. So another issue I like to very briefly discussing is about the short simulation strategy and the process level collaboration. This is the two issues. First is why a short simulation? Because, as I mentioned, we have done 1,100 simulation. Each simulation even 5 years, which still we feel very expensive. It's very hard to afford for most of the modular centers. So we are trying to find some alternative way can more efficiently conduct this UQ type simulations. The second issue is why the process level collaboration. We had some discussing in the past few days. Our collaboration work currently more focused on the response variable like precipitation or temperature. But we know many components, many processes in the climate model could contribute to the precipitation. Even your model using the statistical method to get a very good or perfect precipitation, which can match the observation. But it's very possibly because of the long reason, because of the compositing error from multiple processes. So using this type of model, we are lacking the confidence using this type of model to project the future climate if the process level understanding or process level representation in the model, for example, for cloud or convection or radiation is not right. That's maybe also the reason why every model is very good match the observation in the present day, but when they project in future, they have a big spread because those process level evaluation not really carefully have been done. So that's our philosophy. Like we like to start in the calibration when we develop a new model from the process level, especially like a cloud. And why is this good work? Usually we will do a climatology simulation. We have a single long simulation. Now we propose to do a couple of short ensemble simulations. Another advantage for those type of short ensemble simulation is for the current leadership computing, high performance computing. They like you submit a job using the thousands of the nodes of process. For the short ensemble simulation, we can bond those simulation together, submit one job. That's what we did actually. We run the 1,000, 5,000, 4,000 simulation within 1 or 2 days. We can get this done. But if you run the long simulation, you're not able to get this done so quickly. So this idea is based on hypothesis that for fast process, especially this related to clouds, are major source of the bias in the current climate models. This is a transpose EMIP or CAPT framework, which is originally developed in the UK. They believe that for a good climate model, they first have to be doing good in the weather forecast. It's also consistent with the idea like Shukla mentioned about seamless forecast at different scales. So they found that for the different models, they compared 5 different global models. So they found that the global mean total cloud fraction already seems to converge after 1 or 2 days simulations. So the right side is more clear. This is a sensitivity experiment to look at the impact of the time step. This is a difference of the 2 simulations with 4-minute time step and 13-minute time steps. We can see the difference. But this is based on the 5-year average. We do the same thing, also look at the time step impact, but we're using the short simulations. So we can see at the day 3, we already can see those signals, which is especially very similar with those 5-year simulation. For example, if you look at which means if you want to look at the total cloud fraction difference, we may not necessarily to do 5-year simulation. Rather than instead, we can maybe only do a few days simulation for those fast process, which can efficiently, significantly reduce the computational time. So we have done some work based on the past few years experience in UQ, and in this task, and we identify a region, focus region, so-called GPCI cross section. Why this is why we just look at precipitation is, as I mentioned, we like to do the process level understanding. This transaction is very good to look at the different cloud regime. From here, this side, this nearby the continent side is more straight from cloud, low cloud, or shallow cloud. And also this type here is more deep convection type cloud, and also have a transition from shallow to deep. So along this transect, which can allow us to look at a different cloud regime, and which is good for process level understanding for different cloud type. So I will very quickly skip those, and this is basically similar. We focus on 6 parameters just as examples, and mostly related to the shallow and turbulence. And we do the kept handicap simulation for just 10 days each simulation, but we do the 128 examples. And here is some preliminary result. This is dependence of the model sensitivity on cloud regime. This is relative contributions, total variance. We can see this is the latitude along this transect. So which you can tell the different color represent the different parameter, and this length is the relative contribution. So basically you can tell us under the different cloud regime, and the parameter sensitivity is different. For example, in the shallow part, the yellow, which is parameter 1, parameter 5 seems play more important role, but in the deeper part, the green, which is parameter 4, play more important role. This basically tells us the dependence of the sensitivity on different cloud regime. And the second is about the time evolution of the sensitivity. Because one of our goal when we do the short simulation is we try to figure out how short is good enough to look at some fast response. So this is a sensitivity for the shallow convection. This is, I think, is a short wave cloud forcing, how the sensitivity change with the time. We can see after 1 or 2 days for the shallow convection part, it's very stable already. So which means we even not necessary to do 10 days, we can do it 2 or 3 days. That's good enough to look at the sensitivity for this cloud forcing. But for the deep convection part, and we can see even within days there were some changes. At the beginning part, the parameter 4 seems more important, but the later on part, parameter 2 is more important because of the interaction between shallow and deep. So this is some preliminary result, and I will skip those part. And yeah, the next section is about aerosol effect. As I just briefly mentioned, a traditional way to look at the aerosol impact is we just do 2 simulations. One is control and one is sensitivity. In sensitivity round, we could either including aerosol or double the aerosol, and the control one even without aerosol or just the standard presented color aerosol. Then look at the difference. Actually, Philip and I, we started working on aerosol in 1997. We developed the first aerosol component in regional climate model when we were working together at NCAR. And in this study, actually, using the framework we just introduced, we have ensemble simulation 200 or 100 simulation, which can allow us to look at not only the just the difference between sensitivity and the control simulation, but also we can look at how responding of the interest variable to the emission factor, for example, for the sulfur dioxide. So a little bit more detail here is similar as the previous table, but this table including the parameters in both in cloud microphysics, and also this part is all about emission factor for the dust, for the sea salt, for the sulfur, for the black carbon or organic carbons. So basically we're using the emission factor as the one parameters, like the model uncertain parameters. And this is the default values, and also we have a low end and a high end. The low end we often use as a 0, no emission. And the high end is doubled or sometimes 3 times larger. And the sampling approach we're using quasi Monte Carlo, and this is 16 parameters totally. We run the 250 sample set, so each parameter is sampled 250 6 times, and each simulation also similar. In 5 years, we look at the last 4 years. I just, because of the time limit, I just show one slide, which summarizes some result, or maybe 2 slides. This is AOD, Earth optic depth, change with the emission factor of SO2. Certainly, with the emission increase, we can see the AOD increase almost linearly, and not surprising. This is a difference.
And these simulations, how long? How long are these simulations?
5 years.
These are 5 years.
Each simulation 5 years. Yeah, we have 256 simulation. We divided the 256 simulation into 8 groups. Each group has 32 simulations. Basically, the variance in this each group or each being is representing the variability contributed by the other parameters rather than CO2 emission, because this is x-axis is CO2 emission from low to high. So we can see with the increase of CO2 emission, AOD almost linearly increased, and this is a spatial pattern of the AOD difference between those groups being 8 and being 1. And it's similar for shortwave forcing and temperature and precipitation. I'm not going to look at the details, and also we look at the liquid water pass, which somehow can represent the LSO indirect effect or LSO cloud intention effect. The second slide is because we're debating the LSO emission fact and cloud microphysics parameter simultaneously, which allow to look at the relative importance of the cloud parameters and emissions. So this one for different, this is clear sky, top of atmosphere net radiation flux. We can see the emission fact for the solar and also for PC contributing most. And this is all sky net radiation flux. And this is the cloud forcing. For the cloud forcing, we can see that this blue parameters which contributing the most to the variance of the cloud forcing. And for the AOD and also the emission factor contributed most. But for the cloud drop number concentration and the liquid water pass, actually the cloud microphysics parameters contributed most, which can tell us the uncertainty in those cloud properties will affect our confidence looking at the LSO factor. But because here we tell us those parameters, uncertain parameters in cloud scheme will have a big impact on when you quantify the LSO fact, as I showed in previous slide. And we only listed those in microphysics. Certainly we have other uncertain parameters in the cloud process. So this is first part and about the inverse modeling sensitivity analysis. We don't need to observation, as I just emphasized. We just look at the model performance. And the second part I will very briefly go over is inverse modeling, calibrating the model, how we calibrate the model. Again, I first still using the CAM5 model as an example. You certainly can apply this approach to your own regional global model. The issue, the science issue here, also our motivation is when we look at the precipitation, global mean precipitation, we can find a very similar pattern for the total precipitation. By the way, this bottom-wise total precipitation, this first row is convective precipitation, and this is large-scale or straight-form precipitation. If we look at the total precipitation between observation and the model simulation, which is often we only do, we can find a very good pattern similarity, and also magnitude, although the model is overestimated, but the overall result is not bad. But if we really look at the ratio of partitioning between convective precipitation and the large-scale precipitation, we can see the model actually almost, in CAM5 at least, almost 90% of the precipitation is contributed by the convection scheme. And but the observation shows a different story. It's almost half 50% by convective precipitation and 50% by streamfall, although the total precipitation is very similar. These have some important implication. So our strategy is for course we identify the 1, 2, 3, 4, 5, 6, 9 parameters we believe that are important for the precipitation, and we using the cost function based on the tile diagram, which including the bias standard root mean square bias and also the spatial pattern calculation. We're using this as a cost function, and then this is from the Charles Jackson's pioneer work in this using the so-called MVFSA static sampling algorithm to calibrating the model performance. So I'm not going to, I think Charles already introduced those, and I'm not going to talk about more detail. If I using one sentence to summarize those, the difference with previous sensitivity analysis is for this inverse modeling or calibration work, we need to run the simulation one by one rather than simultaneously, like the sensitivity analysis there. You can in advanced sampling all the parameter space. Here is not. Here, key step is here. After each simulation is done, you have to evaluate them using the observation and calculate the scale score or cost function. So if you found the parameter set you set in the new simulation is more, the resulting result is better than the previous one. Basically, you have more likelihood to select those new parameters in the next round simulations. If not, if result getting worse, not totally no chance, but you have a lower likelihood to choose a parameter space around that parameter set. This is basically idea. I'm not sure if I
mean, it's just phasing and calibration.
Yeah, many people already know basically, but some of them may know. So okay, this is a result, and we can see after our calibration, we can see the partitioning between. This is new result based on our models. We can see the partitioning or the ratio is much reasonable than the default simulation. If we look at the right side, the black is observation and red is default, and blue is optimized. We can see the precipitation distribution is much. This is along the latitude. I think it's much reasonable, and also we look at the PDF of the daily precipitation as a function of rain rate. So we can see over the different regions like the ITC. In the default one, it's for the both low end light precipitation and the extreme high precipitation. Both are not right. Now the new simulation with the optimized process getting much better agreement with the observation for most of the tropical regions. And also, although we're only calibrating precipitation in our metrics for cost function calculation, but also this improvement in the partitioning of convecting precipitation versus large-scale precipitation have impact on the circulation. I think the reason is because of the diabatic heating change. If you change the ratio of deep convection and strength of cloud, it changes the diabatic profile. For example, the latent heat will change the diabatic heating, so have an impact on the circulation. We can just see one example. This is in the default simulation minus observation. We can see the warm color bias in the circulation, and this in the optimized simulation we can see the opposite sign, which means the bias in the circulation in the default one already being reduced. So I'm not going into detail. Here is a summary slide about the impact. So and also we have done, this is based on the global model Qian. We also have done a few case study with a regional climate model like WRF. And basic procedure is the same as for the global model Qian. Certainly we have selected different parameters because the convection scheme is different. In this case, it's a KF scheme. And so we have the model configuration and here, and also different region. So one difference for global model and the regional model is, we have to do those with a focused reading. So very naturally, you would ask a question: if you get optimized parameters based on the domain region 1, those results or those parameters can be transferable when you change mobile reading to one to another. Second issue is how because different group may use a different spatial resolution, so how those optimized parameters will be transferable or not when you change the spatial resolution from one to another. To address these two questions, I think everybody would ask. We have done the repeated those similar optimization process or calibration process over the using the WRF over the different regime. One is here SGP region, another is North American monsoon region, and also we did another set of simulation with different spatial resolution from 50 kilometer to 25 to 12 kilometers. So we can see the parameter response, the model performance response, even very at least the trend is no change when you cross the spatial resolution, and also have a similar response for different regions. So here is the summary. And the last study is actually conducted by Li Weizhou here, and he was visiting me a few years ago. He using RegSim 3 because I know quite a few people in this room are using RegSim 3. He tried to calibrating the MIT cumulus parameterization over the Codex East Asia regions, and he selected 7 parameters. He believed that's very important for the computation. And just one slide to summarize the results. It's similar as my previous slide about the WRF simulation. You can get the spatial pattern much better. This is observation, and this is the default one. We can see the large bias over the oceans, and this is a calibrated simulation. You can see still some bias, but its spatial pattern is much better than the default one. And if you look at the PDFs, we also can see the significant improvement in the spectral precipitation pattern. So here is a summary, and we believe uncertainty quantification methods and frameworks such as the forward and the inverse modeling can be very useful for better understanding the model behavior and the physics process to help model development or improvement, and which can guide and handle model tuning and collaborating, and also can be useful for the quantify the impact of this project forcing like aerosol or greenhouse gases in a more robust way. And process level collaboration like the cloud convection is critical for getting the right response for the right physical reason. And the transferability of sensitivity and the parameter tuning across physical process, spatial scales, and the climate regime are needed to be further investigated. Although we published a paper 2 years ago, and I'll show a start here, but I think this issue needs to be further investigated. And I know some of participants here, they are applying the reading of RegSim 3 or 2 for their own reading. So I think this is a good project you can exercise when you go home after this workshop. You already learned some tools, sampling tools, and some inverse modeling tools by the lectures and by the hands-on lab. So if you have some problem, you can ask our lecturers after you come back even. So you can start some exercise to apply this. Like for example, if you already run the RegSim 3 or 4 at your home, and for your specific reading you are interested, you can try to calibrate your model performance, because I believe you have some observation over your reading, and see and compare with other readings results, see how those issues can be addressed. Maybe we can coordinate some like model intercomparison for UQ model intercomparison project to organize those kind of activities, which is very practical. So because the goal of this workshop is we hope that everybody, when you go home, you can practice and to really get something done and, for your own interest. So that's all I want to say.
Okay, thanks for the talk. All this example is basically focusing on the atmospheric models. What about the ocean component?
Okay.
Because the ocean models is generally much more difficult to tune, right? Because they have some boundary condition, they have different effect, they have long-term circulation or something like that. Mm-hmm. So can we use this kind of things also for the ocean component?
Yeah, certainly. You can use this framework for the ocean modeling or land surface modeling that Jason introduced. You say ocean modeling or ocean tuning is difficult, but actually no model is easy to tuning, right? The atmospheric model also very difficult.
But at least the atmospheric models can give much more quick response to your parameter change.
Right. This is a very good question about the efficiency, because ocean modeling needs to be run longer time period. Sometimes it's really hard to afford for the computer, right? Computation resources. So that's why last point I want to make is more efficient strategy for modeling, evaluation, and tuning need to be further explored.
Also,
in the ocean community, you have different. I'm not familiar with the ocean modeling, but I think this is an important issue if we want to collaborate in the
also,
ocean.
we have less observation in the ocean.
Yeah.
So less dense. Also, in the temporal scale is not so long.
Yeah.
So
actually, there are fast processes in the ocean also, like mixing, and that can be tuned just as fast. And they're very important. But you're right, in general, there are slow processes. Mixing is very important.
I mean, people do accelerators in the ocean, but I always think that it's, I don't think anybody's ever been totally satisfied with that. So I think it's a major problem.
It's a challenging issue because today what I introduced is only the EMIP type simulation. We prescribe the SST, and how we can use those parameters, whether or not we can use those tuning parameters for the coupled mode. We don't know how. This afternoon maybe we will have a little bit discussing how we can tune in the coupled mode.
Maybe. This is an example of the challenges, because I think that the timescales in the ocean are so long. The implications of changing a mixing parameter is significant, of course, on day to week to month, but then centuries to millennia. You know, as the changes at the surface accumulate, it will make its way to the deep. I think we tend to not worry so much, let's say, about the deep ocean equilibration, but at some level, you know, maybe it's important. How to do this, especially if it interacts with the changes in the atmosphere, changes in wind stress over the ocean. Well, you know, it's hard. I don't know how to do this problem. We'll talk about it this afternoon.
of course, tuning the atmospheric component will also affect the ocean component, because if you get much more accurate wind, heat flux, or something like that, of course it will improve the ocean component. But again, there's some missing part in the ocean.
Yeah, totally agree with that. Totally. Yeah.
Thanks. I guess related to points 3 and 4, you can extend a lot of these statistical methods to combine output from cheaper, fast simulations and more expensive ones, typically at higher resolution. So do you make use of that at all, or have you?
Yeah, I think this is a very good point. This depends on what the science issue of interest or what variables of interest. Some fast process is okay, like cloud, maybe we can use in the short simulation. But some others may not be able to use in the short simulation, some other slow process. So In the surrogate model, model is another alternative way. If we can train and get a very good surrogate model, we can use the surrogate model to tune it because it's very fast, right? We can run very efficient. But the question is whether or not we can get a very well-trained surrogate model.
Yeah, I guess I mean in creating surrogate models, you'll incorporate.
Yeah, and then another disadvantage for surrogate model is maybe you can build up a very good surrogate model for the global mean precipitation. But for climate modeler, we not only care about the global mean, right? But we also care about the spatial patterns, spatial variability, which make it more difficult to using the surrogate model over different regions. Lunch and
oh, 2 o'clock?
Yeah, 2 o'clock we will have 1 hour discussing, and then we'll have closing remarks. Please be here if you don't have to leave, and you will get a surprising gift.
Really?
See?
Is it surprising?
I don't know.
It's expected, right?
I don't know.